Now, I would like to introduce how the nominal diameter and wall thickness are linked within the table. The table starts from a nominal pipe size on the left, the nominal diameter in inches, and leads to each schedule number, which in turn specifies the wall thickness t-value. A point of caution here is that the nominal diameter is a nominal dimension, not the actual outside diameter. The actual outside diameter, OD, must be checked in a separate column. Additionally, both carbon steel series schedules and stainless steel series schedules are included within a single nominal diameter row. Once the t-value is determined, the metal cross-sectional area and the pipe weight per foot, or LB/FT, can be calculated. Therefore, the design flow proceeds in the order of selecting the nominal diameter, choosing the schedule, verifying the wall thickness, and then determining the inside diameter, cross-sectional area, and weight.
This slide is a table summarizing the role and principles of the outside diameter column, which represents the actual outer diameter of the pipe. The key point is that within the same nominal diameter, the outside diameter remains constant regardless of the schedule, ensuring compatibility with fittings or flanges. For example, the outside diameter of a half-in pipe is 0.840 inches, which is set larger than the nominal figure. Please refer to the remaining detailed figures in the table during design, and I recommend verifying the nominal diameter first, and then reviewing the flow cross-sectional area and component compatibility based on the corresponding outside diameter value.
I will explain the units and application of the outside diameter column. This table contains the standard outside diameter dimensions according to ASME B.20.1 and B.36.19 specifications, as well as the principles for area conversion using them. For example, the cross-sectional area can be found by substituting the outside diameter value into the formula pi divided by 4 times the diameter squared, and the transverse internal area value, denoted as square feet, is equivalent to cubic feet per foot, making it useful for volume calculations. Since the remaining figures vary depending on design conditions, please find the necessary specifications in the table and use them as reference dimensions when designing insulation, painting, or support spacing.
This slide is a reference table summarizing the outside diameter and wall thickness data by schedule for 3 inches to 4 inches piping. It shows the principle that even as the nominal diameter increases, the wall thickness for 5S and 10S starts identically at 0.083 and 0.120, and the wall thickness increases as you move to higher grades, such as standard or extra strong, thereby increasing the pressure rating. For example, the outside diameter of a 3 inches pipe is 3.500 inches, and the wall thickness, based on the standard grade, is 0.216 inches. Since the remaining detailed figures vary by design condition, please first verify the outside diameter of the corresponding nominal diameter in the table, and then refer to the wall thickness value of the required schedule to calculate the inside diameter and flow area.
Now, I would like to introduce the item representing the metal cross-sectional area in the piping data table. Of metal, or area of metal as written in the original text, refers to the cross-sectional area occupied by the metal, that is, the pipe wall, when the pipe is cut transversely. This item forms a group in the table along with the transverse internal area, and the unit of area is expressed in square inches. Since the metal cross-sectional area is the value obtained by subtracting the inside diameter-based cross-sectional area from the outside diameter-based cross-sectional area, it increases as the wall thickness T becomes thicker. Furthermore, this metal cross-sectional area value is a very important item as it serves as the basis for calculating the weight of the pipe per unit length, or pounds per foot.
Following the previous item, I would like to introduce the metal area item, which is expressed in square inches. In the header of this section, square inches, transverse internal area, and area are written together. Of metal appearing in the body refers to the transverse cross-sectional area occupied by the pipe wall metal. The notation square inches clarifies that all area figures in the table are based on square inches. Here, the transverse internal area represents the area of the internal passage where the fluid actually flows, while the area of metal represents the area of the metal surrounding that passage. Adding these two areas for the same outside diameter results in the total cross-sectional area based on the pipe outside diameter, and the two values complement each other.
Finally, I would like to introduce the area header and the application of the metal cross-sectional area. The header of this item is marked as square inches and area, and the body value of metal refers to the cross-sectional area of the pipe wall metal expressed in square inches. By multiplying this metal cross-sectional area value by the density of steel, you can find the weight of the pipe per unit length or pounds per foot. One point to note is that as the schedule numbers, such as standard, extra strong, double extra strong, and 5S, 10S, 40S, 80S, increase, the pipe wall becomes thicker, and the metal cross-sectional area increases accordingly. Therefore, even for the same outside diameter, the metal cross-sectional area and weight vary by schedule, so this value is used as basic data for pipe support design and load calculations.
I would like to introduce the column configuration of the piping data table. This table provides the internal transverse cross-sectional area of the pipe in square inches. It also shows the weight of water per foot of pipe in LB/FT pipe, which tells you how heavy the water filling the inside of the pipe is per unit length. The inside diameter is denoted as D and should be read in inches. Since these area, water weight, and inside diameter values are key figures used directly when calculating CV or estimating the pressure drop of the piping, it is best to remember them as a group.
Now, I would like to introduce the inside diameter column of the piping data table. The inside diameter refers to the inside diameter, denoted by the symbol D, and the unit is inches. The inside diameter is the most basic dimension that determines the cross-section through which the fluid actually passes. Even for pipes with the same outside diameter, the inside diameter D varies because the wall thickness differs depending on the schedule number and nominal pipe size. The transverse internal area is calculated from this inside diameter value, which then leads to calculations for flow velocity, flow rate, and pressure drop, so you can consider it the starting point for all piping calculations.
Finally, I would like to introduce the inside diameter and water weight columns of the piping data table together. The inside diameter is denoted as D in inches, and the water weight is provided in pounds per foot of pipe, or LB/FT pipe. Looking at the calculation flow, the transverse internal area is derived from the inside diameter D, and multiplying this by the density of water gives the weight of water per unit length. This water weight value is used directly in load calculations for pipe support design or hydro testing, because it indicates the load when the pipe is completely filled with water. As the inside diameter increases, the amount of water contained increases even for the same length, significantly increasing the water weight. Therefore, referring to both columns together allows you to quickly estimate the weight of the pipe when filled with water.
This slide contains cross-sectional area and weight data for 3 inches to 4 inches, piping based on ASME B36.10M and B36.19M specifications. It shows the correlation where the inside diameter D decreases and the metal cross-sectional area increases as the pipe wall thickness increases. For example, the inside diameter for the 3 inches series decreases from 3.334 to 2.300. In the case of the internal flow cross-sectional area, it ranges from 0.06063 to 0.02885 square feet, which is used identically as the volume per foot value. Rather than listing all figures, please first verify the specifications of the piping you are designing and the thickness grade, such as STD or XS, and then refer to the corresponding self-weight and fill water weight.
I would like to introduce the sources and notation conventions for the continuing pipe data tables. The identification, wall thickness, and weight values in these tables are extracted from ASME B36.10M for carbon and alloy steel and B36.19M for stainless steel. To summarize the 3 abbreviations appearing in the table, STD stands for standard, XS for extra strong, and XXS for double extra strong pipe. Additionally, the transverse internal area values listed in square feet can be read directly as the volume in cubic feet per foot of pipe length. Since this convention is applied consistently throughout the table, you can use the cross-sectional area values immediately to calculate the volume held within the pipe.
Next, we turn to pipe data details.
I will now introduce the header area of the pipe data table. This section is the header that defines the column titles, consisting of first, the identification item, second, the nominal pipe size in inches, and third, the wall thickness item. Wall thickness is denoted by the variable T and is measured in inches. The actual numerical rows corresponding to each pipe specification follow beneath this header. Therefore, this slide serves as the reference point for the column structure used to read the subsequent data.
I would like to introduce the wall thickness column among the pipe data table headers. This column represents the thickness of the pipe wall, denoted by the variable T in inches. Following the identification and nominal pipe size columns seen previously, the wall thickness values corresponding to each pipe specification are organized in this column. Since thickness T determines the difference between the inner and outer diameters, it is a key item that serves as the starting point for calculating cross-sectional area and weight.
I will now introduce the nominal pipe size and wall thickness columns of the pipe data table header. This area presents the nominal pipe size in inches and places the corresponding wall thickness T alongside it. The unit for wall thickness is also inches. By reading the nominal size and thickness as a pair, you can intuitively understand how the thickness increases as the schedule number rises for the same outer diameter.
I would like to introduce the outer diameter column of the pipe data table header. This column represents the outside diameter of the pipe in inches. An important characteristic of the outer diameter is that it remains constant even if the schedule number changes, provided the nominal pipe size is the same. In other words, when the pipe becomes thicker, it is the wall that increases, not the outside. The inner diameter D can be found by subtracting twice the wall thickness T from the outer diameter. This outer diameter column is used in conjunction with the schedule number columns for stainless and carbon steel to link which schedule has which thickness within the same outer diameter.
Now I will introduce one of the core items of the pipe data table, the outside diameter. The outside diameter refers to the diameter measured to the outer surface of the pipe, and the unit of measurement used in the table is inches. Please keep in mind that unlike the nominal pipe size, or iron pipe size, which represents a nominal size, the outside diameter is an actually measured value. This outside diameter value is a critical figure used as the basis for calculating the wall thickness and inner diameter for each schedule, which we will cover later.
This table is a reference showing the relationship between pipe wall thickness based on nominal pipe size and schedule number. For example, in the row for an outer diameter of 5.563 inches, you can see that as the schedule number increases, the wall thickness gradually increases from 0.109 to 0.750 inches. For stainless steel, standard specifications such as STD, XS, and XXS are applied along with classifications from 5S to 80S. Since detailed values vary depending on design conditions, please first verify the nominal pipe size and then select and utilize the wall thickness according to the required schedule number.
Next, I will introduce the area items provided in the pipe table. The table presents the transverse internal area along with the area of metal. The internal area refers to the cross-sectional area of the path where the fluid actually flows inside the pipe, and it is used to calculate flow rate and velocity. On the other hand, the area of metal represents the cross-sectional area occupied by the pipe wall, or the thickness of the pipe, and is used to determine the weight or strength per unit length of the pipe. Please remember that these two areas are calculated from the outer diameter and wall thickness and play complementary roles in pipe design.
Now, I will introduce the cross-sectional area items in the pipe engineering data table. This section consists of the column headers for the table on page 251, and all area values are in square inches. First, the transverse internal area refers to the cross-sectional area of the path, where the fluid actually flows inside the pipe. Next, the area of metal refers to the cross-sectional area of the metal forming the pipe wall, which serves as the basis for considering the strength and weight of the pipe. Both areas are expressed in square inches and are organized in the table by nominal pipe size and schedule number. The internal cross-sectional area is used for CV calculations or finding flow velocity, while the area of metal is used for pressure rating and weight estimation. Once the outer diameter and wall thickness of the pipe are determined, These two areas are naturally calculated geometrically.
I will now introduce the area of metal column in more detail. The unit for this value is also square inches. The area of metal refers to the cross-sectional area of the pipe wall metal. You can understand it as the area of the circle drawn by the outer diameter minus the area of the circle drawn by the inner diameter. As the wall thickness increases, that is, for higher schedules like XS or XXS, this metal area increases. This value is the direct basis for calculating the weight per unit length of the pipe, or pounds per foot. Even for the same nominal pipe size, the value differs depending on whether the schedule number is 40S or 80S, so you must check the schedule in the table. Ultimately, this area of metal is a key indicator for evaluating the pressure-containing capacity and mechanical strength of the pipe.
Finally, I will introduce the water weight and inner diameter items. This section contains the headers for the water weight and inside diameter columns, along with the areas in square inches. Water weight is the weight of water in pounds per foot when the pipe is completely filled with water for a length of 1 foot. The inside diameter represents the inner diameter of the pipe in inches, denoted by the symbol D. This inner diameter D is directly linked to the internal cross-sectional area. As D increases, the flow cross-section also increases, and the weight of the water filling it also increases. Water weight is used to calculate dead loads in pipe support design or load calculations. Meanwhile, even if the outer diameter is the same, if the schedule is higher and the wall is thicker, the inner diameter D becomes smaller, and the water weight decreases accordingly. This inner diameter D is a very important value that serves as the basic input for flow velocity, pressure loss, and CV calculations.
This slide is a pipe inner diameter data table based on the ASME B.20.1 and B.20.1 standards. It shows a structure where the inner diameter value is determined by the nominal pipe size and schedule number. For example, when the NPS is half an inch, the inner diameter value gradually decreases as the schedule number increases. For stainless steel, please check the inner diameter by applying the S-series schedule such as 5S or 10S. Since not all values are listed, I recommend that you first verify the material and schedule number of the target pipe during actual design, and then accurately reference and utilize the corresponding inner diameter value.
Here, I will introduce the relationship between the water weight column and the inner diameter column of the pipe table. The D in the table header, as before, represents the inner diameter of the pipe in inches. Water weight, or the weight of water per unit length, is the value expressed in pounds per foot for the weight of water that can completely fill 1 foot of pipe. As the inner diameter increases, the cross-sectional area increases, so the amount and weight of water contained increase for the same length. This water weight value is derived data calculated directly from the inner diameter and is used as basic data for calculating loads when filling the pipe with water, during hydrostatic testing, or for weight calculations during flushing.
This table is a reference showing the correlation between cross-sectional area and weight according to schedule changes for 5 inches and 6 inches pipes. For example, in the case of a 5 inches pipe, as the schedule becomes thicker, the inner diameter decreases from 5.345 inches to 4.063 inches, and the pipe weight increases from 6.36 to 38.55 pounds per foot. Please check the remaining values directly according to your design conditions, and keep in mind that as the rows of the table go down, the schedule becomes thicker when referencing the values for the required specification.
This table is a detailed reference for the pipe specifications and notation conventions we discussed earlier. For example, abbreviations like STD and XS refer to wall thickness grades such as standard and extra strong, and the cross-sectional area values listed in square feet are equivalent to the volume in cubic feet per foot of pipe length. Rather than listing every value, I recommend that engineers first determine whether the material of the pipe they are designing is carbon steel or stainless steel, and then refer directly to the necessary values according to the ASME B.36.10 or B.36.19 standards. This table continues on the next page.
In this chunk, I'd like to introduce the wall thickness column in the pipe data table header. The lowercase t in the header represents the wall thickness in inches. The table defines each row by combining the identification information and the nominal pipe size, or NPS, in inches on the left. Even for the same nominal pipe size, the wall thickness value, T, varies depending on which schedule number you choose, and once this wall thickness is determined, the inside diameter, metal cross-sectional area, and pipe weight are calculated in sequence. This header structure is applied commonly to the carbon steel, alloy steel, and stainless steel tables.
Here, I want to explain the relationship between the wall thickness column T and the schedule number. T is the value representing the wall thickness of the pipe in inches, and in the table, as the schedule number increases, this thickness value also increases. Terms like standard, extra strong, and double extra strong are traditional notations corresponding to specific thickness series. As the wall thickness T increases, while the outside diameter remains fixed, the inside diameter D decreases, and the metal cross-sectional area and the weight per unit length of the pipe increase. Therefore, this wall thickness value is used as a key dimension in determining the pressure rating and strength design that the pipe can withstand.
This slide is a data table defining the relationship between the nominal pipe size, NPS, and the resulting wall thickness T. For example, if the nominal pipe size is 1/8 inch, you can see that the wall thickness value differs depending on whether the schedule number is 10S or 40S. Rather than listing all the values, please first find the NPS of the pipe you are designing, and then match it with the correct wall thickness T value, according to the applicable schedule. Since this data is based on the ASME B1.20.1 and B1.20.1 standards, I recommend using it as a reference when calculating detailed dimensions.
Next, I'll introduce the outside diameter column of the pipe data table. This column represents the outside diameter of the pipe in inches. The most important characteristic of the outside diameter is that it remains constant for the same nominal pipe size, even if the schedule number changes. In other words, as the schedule gets thicker, the outside diameter stays the same while the wall thickness T increases, which in turn reduces the inside diameter D. Because the outside diameter is fixed, the dimensions of flanges, fittings, and valve connections can be matched, and the outside diameter serves as a key reference value when designing piping systems. These outside diameter values are also extracted from the ASME B1.36.10M and B1.36.19M standards.
Finally, I'll explain the repeating structure of the outside diameter column and how to actually read this table. This snippet is the header for the outside diameter column, showing that the same outside diameter column structure appears repeatedly across various pipe size groups. The entire pipe data table is organized in the order of identification items: wall thickness, T, outside diameter, transverse internal area, metal area, inside diameter, D, and then pipe weight and water weight in pounds per foot. For each nominal pipe size, several schedule rows from OS to XXS are grouped together. In this case, they share the same outside diameter, while only the wall thickness, inside diameter, and weight differ. Therefore, to find the desired pipe, first determine the outside diameter group by the nominal size, and then select the exact row by the schedule. Additionally, please note that the transverse internal area values listed in square feet can be used identically as the volume in cubic feet per foot of pipe length.
This slide is a table summarizing the dimensional data for pipes with outside diameters of 8.625 inches and 10.750 inches. It demonstrates the principle that while the outside diameter is fixed, the wall thickness increases and the inside diameter narrows as the schedule number increases. For example, in the case of the 8.625 inches pipe, the wall thickness varies from 0.109 to 0.906, depending on the schedule. Since all values in the table represent wall thickness in inches, please first verify the material and strength grade of the pipe you are designing, and then refer to the value for the corresponding schedule number.
In this slide, we will look at a reference table summarizing the wall thickness values for pipes with outside diameters of 8.625 inches and 10.750 inches. It shows the principle where the wall thickness increases incrementally as the schedule number increases within the same outside diameter to accommodate high-pressure applications. For example, for the 8.625 inches pipe, the thickness differs between STD at 0.322 and XS at 0.5. Rather than memorizing all the values, please first select the outside diameter that fits your design conditions and then find and use the corresponding wall thickness value based on the required pressure rating.
Next, I'll introduce the table column headings for transverse internal area and metal area. The transverse internal area refers to the cross-sectional area of the actual flow path for the fluid inside the pipe. This value is a key figure used as a basis for calculating flow rate and flow velocity. Meanwhile, the area of metal is the cross-sectional area of the metal part forming the pipe wall, which corresponds to the area based on the outside diameter minus the internal area, and it is used to determine the strength and weight of the pipe. Both values are listed in square inches.
Following that, I'll introduce the item specifying the units for the cross-sectional area columns. This header clarifies that both the transverse internal area and the area of metal discussed previously are provided in square inches. Square inches are the standard area unit used in American pipe specifications, and the units are unified so that these area values can be substituted directly into flow rate calculations or pressure drop estimations without separate conversion. Because the units are clearly fixed, it also helps reduce conversion errors that may occur during the design process.
Among the items in the pipe data table, I'll introduce the area of metal. This value is expressed in square inches and represents the cross-sectional area of the metal part that makes up the pipe wall. The calculation method is to subtract the cross-sectional area of the circle formed by the inside diameter, d, from the cross-sectional area of the circle formed by the outside diameter. Therefore, even for the same nominal size, as the schedule increases and the wall thickness becomes thicker, this metal area increases accordingly. This figure is an important criterion for gauging the strength, weight, and pressure rating the pipe can withstand. Please remember that the unit is square inches, not inches, meaning it represents an area rather than a length.
Now I'll introduce the internal cross-sectional area, water weight, and inside diameter items. First, area represents the flow cross-sectional area inside the pipe in square inches. Water weight shows the weight of the water filling the pipe per foot of pipe length in pounds per foot. Inside diameter refers to the inner diameter of the pipe and is denoted by the symbol lowercase d. As the inside diameter d increases, the internal cross-sectional area widens, and the weight of the water filling it increases accordingly. Therefore, when calculating actual flow rates or estimating the load on the piping, the inside diameter d and this water weight value are referenced together.
Finally, I'll introduce the inside diameter. This value is expressed in inches and is represented by the symbol lowercase d in the table. A point of caution here is that this inside diameter is the actual internal dimension, which is different from the nominal size of the pipe. Even for the same nominal size, as the schedule increases and the wall thickness becomes thicker, the inside diameter d becomes smaller. This inside diameter is the most basic input value when calculating flow velocity, pressure loss, and internal cross-sectional area. Along with the metal area and water weight items we looked at earlier, you can understand that this d value constitutes the core dimensions of the pipe data table.
Now, I'd like to introduce the inside diameter item in the middle of the pipe data table. This column, denoted as d, represents the inner diameter of the pipe and is measured in inches. The value of d is determined by subtracting twice the wall thickness, t, from the outside diameter. In other words, d follows the relationship of OD minus 2t. Since this inside diameter is the actual passage through which the fluid flows, it serves as the most fundamental input when calculating flow rate or flow velocity. Right next to this inside diameter column in the table, you'll find the water weight column in pounds per foot, which is the weight of the water filling the pipe. This allows you to see at a glance that as the inside diameter increases, the amount and weight of the water it holds also increase.
This table summarizes the detailed specifications by schedule for NPS 8 inches pipes, showing the correlation between inside diameter, cross-sectional area, and weight according to changes in wall thickness. For example, as the schedule becomes thicker, the inside diameter D decreases from 8.407 inches to 6.813 inches, and, accordingly, the pipe's own weight increases up to a maximum of 74.69 pounds per FT, since the remaining values vary depending on design conditions. Engineers should first verify the schedule number they intend to apply and then refer to the corresponding inside diameter and internal volume values.
This table summarizes the detailed figures by schedule for NPS 10 inches. Pipes showing the correlation between inside diameter and weight according to changes in wall thickness. For instance, you can see that the inside diameter D decreases from 10.482 inches to 8.500 inches, and as a result, the pipe weight increases sharply up to 115.64 pounds per ft. As other detailed figures differ based on design conditions, engineers are advised to first check the applicable schedule number and then refer to the corresponding cross-sectional area and volume values.
Finally, I'll introduce the sources and notation conventions of the pipe data table. The identification, wall thickness, and weight values in this table are extracted from the ASME B.20.1 and B.36.19 standards. Among the abbreviations in the table, STD stands for standard, XS for extra strong, and XXS for double extra strong pipe. Additionally, this table covers carbon steel, alloy steel, and stainless steel. One point to note is that the transverse internal area value expressed in square feet is equivalent to the volume in cubic feet per foot of pipe length. Please also keep in mind that this table is structured to continue across multiple pages, as indicated by the continued mark.